Hello everyone, today we do Laplace transform and initial value problem. So how Laplace transforms are helping to solve initial value problem. From the last section 6.1, there was one theorem left. So I'm going to kind of finish 6.1 and then move to 6.2. So I'm going to start with the statement that Laplace transform is a linear operator. Is a linear operator. Well, we already remember what is a linear operator. Linear operator is a function which converts a linear combination of vectors, in our case functions, into a sum of linear combinations. Why it's a linear operator? Well, I'm not going to actually prove it, but you remember that Laplace transform is an integral, right? For the integral, if you take the integral from this expression, you can always take the constant outside of the integral first, and you can always split one integral of the sum of two functions into the sum of two integrals. That's why it's going to be a linear operator. How are we going to use it? Well, you already know several functions for Laplace transforms, right? You can combine them together. For example, somebody is asking us, please find Laplace transform of the next function. F of t equals 5e to the power of negative 2t minus 3 sine of a 4t. Well, we do know separately how to transform this and how to transform this. And these two are the constants. So for Laplace transform of our function f, what we are going to have? We are going to have 5 Laplace transform of e to the power of negative 2t minus 3 and Laplace transform of sine of a 4t. Now we can use the formulas we developed in the previous lecture, right? So Laplace transform of exponential function is going to be what? 1 over, supposed to be s minus a, right? Which is coefficient here, like this is my a. So it's going to be s minus 2 and minus 3, and we are supposed to have a over s squared plus a squared, right? My a is 4 here. I'm going to kind of simplify it a little bit, but not much. It's 5 over s plus 2 minus 12 over s squared plus 4. Well, 4 squared is 16 actually, so I'm just going to write down 16. Well, we just found Laplace transform very easily from this expression, knowing that Laplace transform is a linear operator. How did I get? Yeah, that's 3 by 4, right? Okay, I was just looking. Do I miss anything here? Okay, now we are moving to the theorem which I did not prove last class. I'll need to erase everything, so it's going to take me a second. I'm going to pause for a second and then start after erase. Okay, so remember last section or last video I was telling that not all functions do have Laplace transform. Well, why does it happen? Because not for all functions f of t, the integral e to the power of negative st f of t from 0 to infinity is convergent. So what are the conditions on f of t to make it convergent? So how f of t is supposed to look to give us a convergent integral and to have a Laplace transform? First, f of t is supposed to be piecewise continuous on the interval from 0 to some point a. And the second, f of t is supposed to be limited by some exponential function with some coefficient k, which can be kind of basically any number, and some exponent a, which also can be any number. But it's supposed to be less than this function. So you can put 10 billion here and 20 billion here, but it's supposed to be less than this. Not all functions satisfy this condition. So functions supposed to satisfy this condition starting with some number m and to infinity. So for all little t's from big M to infinity, the f of t is supposed to increase not faster than this function. And k and a are the constants, and we can find them or we can define them, but just basically any constants. Then the integral will converge for s greater than a. So a is going to actually tell us from which s we are going to start this function. Okay, I'm going to prove the theorem, and let me just tell you like why do we have these two conditions. Condition number one is telling us that that the function under the integral is going to be integrable. So remember that we can integrate everything which is continuous or piecewise continuous. That's why we require for f of t to be piecewise continuous. Does it mean? It means that function does not go to infinity anywhere in this interval. And second, the end behavior of the function, it does not grow too fast at infinity. It's not like it cannot grow at infinity. It's still like t squared still is going to have a Laplace transform, but it's not supposed to grow too fast. Okay, now I'm going to pause and erase everything and start proof. Well, Laplace transform is going to be the integral, right? I'm going to split it into two integrals. One of them is going to be from 0 to number m, from which actual function starts not growing too fast. And this is just a regular integral. If function is piecewise continuous on interval from 0 to m, it's just going to give you a number, because it's not a proper integral. This is a number, this m is going to be a number too. Function does not go to infinity anywhere. It can only have jump discontinuities. So the first integral is just a number. Just a number. Wow. Second integral can bring us surprises. What I'm going to do, guys, I'm going to do estimations for second integral using my second condition of the theorem. So I'm going to tell that my second integral is going to be less than integral from m to infinity e to the power of negative st, and instead of f of t, I'm going to put my function k e to the power of at, because I do know that my f is less than this by absolute value. Then it's going to be less than just. Now I'm just going to combine two exponential, I'm missing dt. I'm going to just combine these two exponential functions together and calculate the integral and show that it's going to be convergent one. So constant k can go outside this one, right? And that's going to be e to the power of a minus st dt, right? And I'm going to calculate it. Not very difficult, so it's going to be k e to the power of a minus st divided over a minus s, and substitution from m to infinity. Well, guys, we already remember that this goes to 0 at infinity, when t goes to infinity, only if a minus s is negative. So I'm going to write it down somewhere. So a minus s is supposed to be negative, less than 0, to bring actually the term at infinity to 0. If it does not go to infinity, exponential function does not have another option. It has either infinity option or minus or 0 option. So when t goes to infinity, it either can be go to 0 or to infinity. If this is greater than 0, it will go to infinity. If less than 0, then it's going to go to 0. And which means that, well, this is going to be also a convergent or a number. Well, m, substitution of m is not going to make anything bad over here. It's just going to be like m here, and that's going to give you a number too. So very easy. We can see that that's going to be like convergent. Well, again, let me kind of circle it, and I don't want to copy it again. I'm going to just write down e to the power of a minus s, n minus e to the power of a minus s m over a minus s. I think, can you see it? Yeah, you can see it. Okay, so this term will go to 0 when n goes to infinity. Let me put a limit, n goes to infinity. When n goes to infinity, this term will go to 0 only if a minus s is less than 0. This term is just a number. It doesn't go anywhere. It's just like, remember that m is eventually any number like from which function does not grow too much to infinity. Well, we did the proof. So this one is going to be convergent. Convergent for a minus s less than 0 or s greater than a. Remember our condition setup. Integral is going to be convergent for s greater than a. Okay, that's a proof. Now we can move to like how we use actually Laplace transform to solve differential equations, which is explained, I'm hoping, in section 6.2, but I'm not really sure because I still don't have a book. I'm going to just get it tomorrow. Okay, I'm going to stop my video for a second, erase everything from the board, and continue doing Okay, before we start using Laplace transforms to solve differential equations, there is a little theorem which is going to help us to find Laplace transforms of derivatives using actual functions. So, if function f of x is continuous and f prime of x is piecewise continuous on any interval from 0 to a, and f of t does not grow too fast, remember the previous theorem, which means that we do have k, a, and m, which are making this inequality true. And again, they can be any numbers. They can be like 10 billions, for example. It does not matter. If we do have such a number, it means that function is going to fit into this theory. Then Laplace transform of a derivative of this function is going to be equal as multiplied by Laplace transform of a function itself minus f at 0. Very nice, right? We really don't need to differentiate here anything. We're just going to use known Laplace transform of a function multiplied by s and subtract f of 0. So plug in 0 here and find out what is the value. Very nice theorem. I'm going to prove it. Well, the proof is going to, you probably kind of suspect, have integration by parts. I'm going to start proving and then I'll need to erase everything again. So I'm going to make a little stop. Okay, my proof. Well, first I'm going to calculate integral from 0 to a e to the power of negative s of t, st, by f prime t, f prime of t, dt. So if it has only a certain discontinuities, then that's going to be Laplace transform, right? It's the integral is going to kind of exist. There is going to be no question, right? Like if the derivative has only like certain points of discontinuities, then this integral, that's a number, is going to exist. And now let's move to actual Laplace transform then. Give me a second, I'll erase everything from. Okay, so we are going to find Laplace transform of a derivative. And I'm just putting derivative instead of a function here and copying my kernel, and that's integral from 0 to infinity. What I'm going to do, guys, I'm going to take this integral by parts. So I'm going to keep actually right now the limits, 0 at infinity. I don't want to kind of go to actual limit because it's going to make everything longer. So this is already a derivative, right? So I'm going to use it as a derivative, and this one is going to be my function. So my function is e to the power of negative st, and antiderivative of f prime is of course f of t, right? Because, well, if you anti-differentiate this, then minus integral of antiderivative multiplied by derivative of this. Well, derivative of this is e to the power of negative st multiplied by negative s, right? And dt. Well, what I'm going to do, I'm going to put plus here and eliminate this minus. And maybe I should eliminate also parentheses just because, okay, why do we need parentheses if there is no minus now? Well, that's going to be the integral, right? dt. And we are going to take this integral from 0 to infinity, right? I'm going to put my limits from 0 to n and from 0 to n here, and now put over here the limit and say that n goes to infinity. Well, I'm going to kind of do my substitution and show you like what happens to the integral. So first, limit n goes to infinity. I'm going to substitute n here. So it's e to the power of negative Sn f of n minus e to the power of negative as 0, right, which is going to give us actually 1, and this is going to give us f of 0. I'm plugging in 0, plus, I'm going to keep the integral, 0 to n f of t e to the power of negative st as dt. Okay, so let's talk about like first term, this one. What is going to happen to this term when n goes to infinity? Well, if s is greater than a, if s is positive, for example here, then when n goes to infinity, this will go to 0. Function f of n, well, maybe I should just write it down separately. Give me a second, guys. I'm going to use a different color and explain what is going to happen to this term separately below, okay? E to the power of negative Sn multiplied by f of n is less than e to the power of negative Sn by k e a n. I'm using inequality, which I said before, but it's already erased from the board, right? And then I'm going to write down that's k, this expression, e to the power of minus n s minus a, right? If s greater than a means that s minus a greater than 0, then this expression is positive, this goes to infinity, so the whole thing will go to negative infinity, right? And expression like this expression will go to 0. Again, s minus a is positive, greater than 0. This is greater than 0 because it's positive infinity. And altogether, this is going to be negative infinity, and e to the negative infinity goes to 0. This is just a number. So we have actually this term going to 0. This term does not go anywhere, it's just a constant. What is this, guys? For the integral about t, s is just a constant. You can take it outside of the integral. It's just a constant. If you kind of, well, I don't want to copy everything, but you imagine that there is no s, you're going to see that this integral is nothing else than normal Laplace transform of f of t. And we do know that it exists. So let me kind of circle it maybe here and just like, or maybe erase this part. Guys, I'm going to erase this part just because, well, I don't have space. So this blue part explains why this term is equal to 0. Now I'm going to explain why the last term is actually Laplace transform. So now this red part is s integral from 0 to n. Let me put actual limit here. Limit as n approaches infinity, s here, f of t e to the power of negative st dt. Well, if you consider just this integral, this is actual Laplace transform of f of t. So I have s Laplace transform of f of t. Well, now this goes to 0. This is a term which is left over, and this is Laplace transform. So what I have actually is that Laplace transform of a derivative, let me erase this. I'm just going to copy the results on the top and then erase everything, is equal to this one, right? That's your last term, term number 3, s Laplace transform of f minus f of 0. So I proved my theorem. That was a statement of the theorem, and I proved it. Okay, now I'm going to pause and kind of erase everything from the board and continue, start using it. Okay, what is going to happen if I want to calculate Laplace transform of a second derivative? Well, according to my theorem, it's supposed to be s by Laplace transform of what was differentiated to get second derivative. Second derivative is a derivative of the first derivative, right? So Laplace transform of the first derivative minus first derivative at 0, right? And I do have the formula. I can use the very same theorem to consider this one, right? S, and here I have as Laplace transform of a function minus f of 0, and this is just this first term, and I'm copying last term, minus f prime of 0. I'm going to kind of combine these two s together as square Laplace transform of a function minus s f of 0 and minus f derivative of 0. Well, you can see that we can actually get Laplace transform of any derivative of f if you do know Laplace transform of f. It's just like a bunch of like Laplace transform of f multiplied by s squared or cube or whatever, and here s of f of 0 and minus f prime. What if I want to take nth derivative, like in general? Laplace transform of f nth derivative. You don't need to memorize this formula. It's better to remember how the first theorem, okay? Nth derivative is s to the power of n, right? Laplace transform of f minus, and we are going to start, what is this? That's a function, right? It's going to have s minus, n minus 1 multiplied by f of 0 minus s n minus 2 multiplied by f prime of 0. So the power of this is going down, the power, like the derivative, goes up, minus, minus, and finally it's supposed to be n minus 1 derivative at 0, like the last one, right? Okay, not very difficult, right, to find any derivative using this formula. Now I'm going to consider example from the book and solve one differential equation using Laplace transform. And I do know that it's much easier to solve this differential equation just by characteristic equation. I'm using it to show you how Laplace transform is working. Okay, so normally people don't use Laplace transform when it's not necessary, when you can find easier way to do it. But in some cases, there is no way to do it without Laplace transform. But because we are learning Laplace transform, I want to consider first the simple equations, and of course they can be solved by any different method. Okay, here we have initial value problem. Y second derivative minus y prime minus 2y equals 0, y of 0 equals 1, and y prime of 0 equals 0. It's super easy to solve using characteristic equation. But we will use Laplace transform to show how Laplace transform is working. Okay, so I'll start with converting this equation or applying Laplace transform to this equation. So what is Laplace transform of this whole equation? Y second derivative minus y prime minus 2y. Okay. Maybe I'm going to kind of use the property of linearity of this operator and write down that it's Laplace transform of second derivative minus Laplace transform of first derivative minus 2 Laplace transforms of the function. Well, now guys, I'm going to maybe kind of start working with these derivatives, but I'm not going to do anything with the function. I'm going to keep the function for a while as it is, okay? So we remember the formula. Laplace transform of a second derivative is s squared Laplace transform of a function, right? Minus s, the function at 0, right? Minus the derivative at 0. Well, minus, I'm going to do this term, derivative, minus, I'm sorry, I'm going to put parentheses to not mix with minuses. It's going to be s, Laplace transform of y, first derivative is going to give me just y, and y of 0. And the last one is going to be just as it is, Laplace transform of y, and it's going to be equal to 0. Okay, now what I'm going to do, I do know y of 0 and I do know y prime of 0. They are 1 and 0. Let me kind of right now label them on equation. This is 1, this is 0, this y of 0 is again 1. So how am I kind of, if I combine everything together, how it's going to look? Well, first, I'm going to combine all terms with Laplace of y. So I'm going to put Laplace of y, and what we have is s squared, this term, right? We also have minus s. What else we have? Minus 2. Now, this term is going to give me just minus s, right? This term is going to give me 0. This term is going to give me 1. Minus and minus is going to give me plus. And there is nothing more, right? Very nice. Well, I'm going to move, I'm going to separate Laplace transform from the rest. Can you still see? Yeah, I think we can just, I do one more line here. Laplace transform of y equals s minus 1. I'm moving this on the right side, and I'm dividing by the term of Laplace transform minus s minus 2. I think that's the bottom we can see, right? Okay, very good. So you see Laplace transform of my y actually is supposed to look like this. What I'm going to do, guys? I'm going to use my knowledge from Calculus 5b of how to decompose a fraction into simple fractions. To do this, I'll need to erase something from the board. That's going to be first two lines. I'll need to keep this over here because if I don't see it, I won't be able to do decomposition. Erase everything. So I did erase the equation, but because I already extracted all information from it, so I'm going to decompose s minus 1 or s squared minus s minus 2 into two fractions. What is this actually? Can we factor it? If we do factor it, that's s minus 2, what? S probably plus 1, right? Let's multiply. Minus 2 and minus 2 plus 1 is minus 1. Yeah. So a over s minus 2 plus b over s plus 1. Remember partial decomposition. Well, I'm decomposing this expression into simpler fractions. I'll tell you why I'm doing this. So how do we find a and b? Well, you crisscross multiply, bring it to common denominator, and just make coefficients of this polynomial equal to coefficients of this polynomial. I think I'm going to work on this side. That's as plus a plus bs minus 2b. And denominator, I'm not going to kind of multiply. I'm going to just write down s minus 2, s plus 1. I do know that this fraction must be equal to this fraction. Denominators are already equal, right? The numerators must be equal. So terms with s supposed to be equal to 1, right? Because it's 1s here and a plus bs here. So I'm going to write down that a plus b equals 1. And then terms without s, a minus 2b, supposed to be equal negative 1, right? Because it's negative 1 here. So I got a system of two equations, two variables, right? What I'm going to do, I'm thinking that subtract second equation from the first. So a minus a, 0. B plus 2b, that's 3. B equals 1 plus 1 equals 2, so B equals 2 over 3. Well, from where A, because they make up 1, from where A equals 1 over 3. So this is my decomposition. What should I do next with this decomposition? I think I'm going to raise this. I don't know. Or maybe I'm going to just write down that Laplace transform of some function y, which is my solution actually, equals 1 over 3 s minus 2 plus 2 over 3 s plus 1. Now I can erase everything else. Remember that y is a function which I'm searching for, right? What I'm going to do, guys, now, look at my trick. And it's a little bit illegal. We did not do actually explanation for reverse Laplace transforms, but we can do it once to kind of, show how everything works. And then we are going to do everything more legal in future. So, guys, do you know Laplace transform of what is this? Remember that it was exponential function, right? So I'm going to write down that 1 over 3, 1s minus 2, it's actually 1 over 3 Laplace transform of what? Laplace transform of e to the power of 2t, right? Remember, s minus a. And the second one, 2 over 3, 1 over s plus 1. It's 2 over 3, Laplace transform of what? That's also exponential function. E, it's supposed to be s minus a, right? But so my a actually is negative 1 minus t. What I'm going to do, I'm going to take these coefficients inside because I remember that Laplace transforms are. So I'm going to write down that Laplace transform of, well, maybe I should continue over here. But this one is equal Laplace transform of 1 over 3 e to the power of 2t plus 2 over 3 e to the power of negative t. So Laplace transform of my solution equals to Laplace transform of this function, means that my solution equals to the function. And voila, I got my solution. 1 over 3 e to the power of 2t plus 2 over 3 e to the power of negative t. You see? Basically, that's how we use Laplace transform. You see that we did not solve really, we did not integrate anything here, right? We did not solve any differential equations here. We just knew some Laplace transforms and we decomposed some fractions. That's it. Well, we know that solving differential equations is always integration. So where are we missing this integration? We're missing this integration when we say actually that Laplace transform of exponential function equals to this, right? Because once in the beginning we took Laplace transform and it was an integral. Now we are just using a ready formula. So basically we are kind of wrapping integration process into a ready formula. And that's a major use of Laplace transform, helps to solve problems and move them from the field of differential equations to the field of algebraic problems and use of ready formulas, of course. Okay. Well, now we are going to move to properties of Laplace transforms and I'll need to erase everything. Okay. By the way, you see that we incorporated initial conditions right away. We got our solutions with constants. Laplace transforms are solving initial value problems. It does not give you general solution. It's going to solve special initial value problem. But you always can set up any problem as an initial value problem. No? Okay, and just a second, I'll erase everything and we continue. Okay guys, I placed on the board 5 properties of Laplace transform, and we do know at least 3 of them already, how they work. First property, it's a sum of the function is converted into the sum of Laplace transforms. Again, it follows from the property of integrals. So integral of sum of two functions is equal to sum of two integrals. A constant can be taken outside of the integral, means that it can be taken outside of Laplace transform. Well, for derivative, we just prove the theorem, right? The Laplace transform of a derivative, it's s Laplace transform of a function minus f of 0. My 0 looks like 6. Next two properties I did not prove, but I'm going to do it. So, property number 4. If you multiply function by e to the power of at, for Laplace transform, you can find Laplace transform of a function, but instead of argument s, put argument s minus a. And property number 5 is if you multiply your function by t to the power of n, you can actually take Laplace transform of a function, differentiate it n times, and then multiply by -1. That's a little bit kind of strange. These last two properties are not very kind of obvious. I'm going to start with property number 5, and I'm going to prove property number 5. Proof is not long, but I'll need to erase everything from the board. Okay, property number 5. If you multiply function by t to the power of n, and you want to find Laplace transform, it means that you just calculate Laplace transform of function f, which you probably already know, and then differentiate it n times and put -1 in front. The proof. Well, let's consider f of s, which is actually like Laplace transform of f. which is going to be integral from 0 to infinity f of t e to the power of negative f of t dt. Now I'm going to differentiate this f of s by s. Well, because Laplace transform is actually like a derivative, right? That's a function of s. Well, here, because I have two different variables, s and t, I'm going to do a partial derivative by s. ds integral from 0 to infinity f of t e to the power of s dt. Well, from this expression, only one thing depends on s, exponential factors. So I'm going to bring the derivative in and write it down as 0 to infinity f of t. What is derivative of this function by ds? d e to the power of negative st by ds. Well, it's supposed to be negative t, right? E to the power of negative st. Imagine now that variable here is s, so t is minus t is a constant. So you kind of put a constant in front, and that's going to be the derivative. So I'm going to copy it. Minus t e to the power of negative st dt. Now, if you look at this expression and you kind of get rid of the minus, put it in front, you're going to have minus integral from 0 to infinity f of t multiplied by t e to the power of negative st dt. Well, this is Laplace transform of my new function f of t multiplied by t. So I'm going to put that's minus Laplace transform of f of t multiplied by t. So it's kind of this formula for n equals 1. So if n equals 1, then Laplace transform of f of t multiplied by t, if you bring this minus over here, it's going to be just the first derivative and the minus, right? Means that if I put plus here and put minus here, if I multiply these two expressions by negative 1, I'm going to get just minus first derivative. While if you differentiate it more, you're going to have a second derivative and a third derivative and so on. It's just going to give you the same expression. Okay, now I want to consider example first, how it helps, and then kind of move to property number 4, okay? So I'm going to erase everything. So I proved it only for the first derivative, but by induction, it's going to be correct for nth derivative too. So, how it helps? Well, we do know, for example, that Laplace transform of sine of at equals a over s squared plus a squared, right? And now, what is a Laplace transform of t, sine of at? Sometimes, right? Look over here. That's t, and that's sine, right? We take minus 1 because that's like first power minus. And what is Laplace transform? First derivative. So I'll need to do the first. If this is 1 and this is 1, that's the first derivative of sine. What is Laplace transform of sine? Let me write it down in one line. So I'll need the first derivative of Laplace transform of sine of at. First derivative. Well, this is Laplace transform. This is it. So I differentiate it and I'm going to get the expression. So I differentiate it by s. So that's a fraction, right? So I'm going to give me s squared plus a squared. Well, because this sits in the denominator, I differentiate as a composition. That's going to give me 2, right? That's minus 1, so it's going to be minus 2, so it's minus 1. And I'll differentiate this expression, it's going to give me 2s. And because I had a minus in front, this minus comes from differentiation. This minus is going to turn it into plus. I'm going to get 2sa over s squared plus a squared squared. And I got a Laplace transform for a totally different function, t sine, instead of like my just sine knowing the Laplace transform. So if you need a like t squared here, you will need to differentiate this 2 times. Yeah, it's not going to be easy, but it's better than finding like integration by parts. Okay, now let's move to property 4. I'll need to erase everything. Give me a second. Okay, property number 4. If you multiply your function by exponential function e to the power of at, you just actually take Laplace transform of your function f and shift the argument. So how do we prove it? Well, first I write down Laplace transform of this product, right? And put it under the integral with kernel minus st. And then I combine these two exponential functions together. Now, guys, what I can do, well, I can label this one as kind of new s tilde. And then this one, this expression is going to be looking like a Laplace transform of f from argument s tilde. It's a Laplace transform of f, and the argument is s tilde. But what is actually s tilde? S minus 1. So basically, there is not much proof here. I want to consider maybe an example how it helps. Let me do example. I think I'm going to consider a Laplace transform of e to the power of t multiplied by t. How about this? I think that's not a bad idea to do, right? We do know what is Laplace transform of t, so we can apply the formula and kind of find out what is Laplace transform of e to the power of t, right, multiplied by t. So what is Laplace transform of t? Remember that it was 1 over s squared. So we do have, give me a second, yes. My cat is trying to jump over here. Okay, guys, my cat came to help me to destructure a box a little bit. I'm going to wait a second. I think he probably will leave. I don't know. No, you see, that's a real cat lecture. Oh, okay, he's leaving. Give me a second. Okay, good. So guys, my cat left, so we can do it. So what we see is that a equals 1, right? And this Laplace transform of t, and here we're going to be s minus 1, right? Well, what is Laplace transform of just t? Remember, it's 1 over s squared. But if you put argument s minus 1 instead of x squared, we're going to have s minus 1 squared. Sometimes it's helpful, you know. Okay. Well, I don't know. Maybe I should consider one more example, but otherwise I want to kind of finish the lecture because it's already like 43 minutes long. Maybe go back to property number 5, but that's going to take maybe forever. Okay, I'm going to consider one more example on use of property number 5. Already did one, but just one more. And guys, I have some problems for you to solve on your own after you watch the lecture, but I don't know like how much time you're going to have. So find Laplace transform of t square. What is Laplace transform of t square? Question. You know that what is Laplace transform is t or 1. What I'm going to do, guys, I'm going to represent this Laplace transform of t square and over here multiplied by 1. Multiplication by 1. Multiplication by 1. So what it's going to be? It's going to be minus 1 to the power of 2 using property number 5, right? And then Laplace transform of 1 in the second derivative, right? 2 plus 1. You probably still remember Laplace transform of 1. It was what? 1 over s. And the second derivative of it, so it's minus 1 to the power of 2, sorry, missing 2. First derivative of 1 over s, it's negative 1 over s squared, right? And the second derivative is going to be, well, I'm going to convert this one into 1, right? Minus 1 squared is 1. Second derivative is going to be 2 over s cube, I guess, right? We kind of differentiate it one more time, so the square is becoming cube, and it's minus 2, so which are going to put on numerator, this minus is going to cancel. I think that's going to be the answer. Okay, I think that's going to be it. And please look in my notes. I'm not going to copy the lecture in my notes, by the way. That's going to be just a lecture, and that's it. I'm going to give you some notes for extra problems, okay? Thank you, and we are going to finish at this point.